So, let's say you've got a stream of data points coming in over time. Could be anything really. Stock prices, sensor readings, you name it. You can see the numbers ticking by, but how do you figure out the hidden system that's actually making it all happen? If you're used to dealing with static, relational data, that one question changes the whole game. We're not just looking at a snapshot anymore. We're trying to understand the hidden machinery that works and evolves through time. All right, let's get into it. We all handle massive databases, right? So what is it about adding that time component that makes things so uniquely tricky?
Well, these challenges really force you to think differently. First up, observability. The thing is, in the real world, you can almost never measure everything. Imagine a complex engine. You might only get a reading for the output voltage, but what about all the internal temperatures and pressures that are actually driving its behavior? Then you've got nonlinearity, where cause and effect just aren't a simple straight line. And what's really wild is that what looks like random noise might actually be the most important part of the signal. In chaotic systems, you filter that out, you lose the whole story. And finally, these systems have memory. What's happening right now is a direct result of what happened a moment ago, all thanks to feedback.
Okay, that makes the problems a lot clearer. But do we analyze all of these time-based systems the same way? It kind of sounds like some are a lot more unpredictable than others. That's a great question, and the answer is absolutely not. You have to know which type of system you're dealing with because the playbook is completely different. A linear system? It's predictable. It's got one stable state, a fixed point, and no matter where it starts, it always ends up in the same place. The whole system is just one big basin of attraction. But nonlinear systems, they're a whole other animal. They can have multiple stable states called attractors, each with its own basin. And a tiny, tiny change in where you start can lead to a massively different outcome. Think of a raindrop landing just a millimeter to one side of a mountain ridge versus the other. That's chaos. That's sensitive dependence on initial conditions.
This brings up a really critical question then. What if we can't see the whole system? If all we have is that one single stream of data, how on earth can we understand a system that might have dozens of hidden variables?
You've just hit on the core issue, the classic black box problem. In pretty much any system you can think of, the most important variables are either physically impossible to get to or we just can't measure them. We're stuck trying to understand this giant, complex machine by peeking through a tiny keyhole. Luckily, there is a seriously elegant solution. It's called delay coordinate embedding. It's this brilliant mathematical technique that lets us build a complete multidimensional picture of what's going on inside the system, using only that single stream of data we can actually see. And here's basically how it works. You start with your single column of data. Then you pick a time delay. Let's call it tau, and you figure out how many hidden variables or dimensions you think there are. Then, for every single point in time, you create a new, richer data point. You take the measurement now, and you pair it with the measurement from 1 tau ago, 2 taus ago, and so on for each dimension you need. And just like that, what was a flat, boring list of numbers unfolds into this rich, multidimensional view that reveals the hidden shape of the system's dynamics. It's incredible, and it all comes from that one single data stream. Okay, that is incredibly powerful for just understanding a system. But can we push this even further? Can we use modern tools like AI to actually predict what the system is going to do next? You bet. That reconstructed data is the perfect foundation for predictive tools. Once we've uncovered the system's true shape, its true dynamics, we can train a model, like a neural network, to learn those underlying patterns and tell us what's coming next. One great way to do this is with a time delay neural network, or a TDNN. You can think of it as a regular neural network, but with a short-term memory. By adding these little time delays, the network isn't just seeing the input right now, it's seeing a small window of recent inputs. That allows it to spot patterns as they unfold over a short period of time. But for even more power, you can use recurrent neural networks, or RNNs. See, instead of just a fixed little window into the past, RNNs have internal feedback loops. This lets information persist and literally cycle back through the network. It creates a real internal state, a genuine memory, which gives them the amazing ability to process sequences of basically any length, because they can remember important stuff from way, way earlier. And with these kinds of powerful memory abilities, TDNNs and RNNs have become the go-to tools for pretty much any task that involves a sequence. We're talking about everything from forecasting volatile stock prices and powering the voice recognition on your phone to modeling incredibly complex dynamic systems and building the autonomous control systems of the future. So, after this whole journey,
from the fundamental challenges of time all the way to these advanced AI forecasters. What are the really key things to remember from all this?
Okay, so here's the bottom line. Analyzing data over time isn't just about adding a timestamp column. It's about changing your entire approach. The biggest takeaway is that even if you only have a single limited stream of data, you have the tools to reconstruct the complex hidden machinery that's running behind the scenes. By figuring out if your system is linear or not, and then using these powerful techniques, you can stop just reacting to data and start truly understanding and even predicting the dynamics that drive your world.
And that's our look into the dynamic and often hidden world of time series analysis. If this explainer helped you see the hidden patterns in your data, do me a favor and share it with a colleague. And of course, subscribe for more breakdowns of complex topics. The next time you see a simple line chart, I want you to ask yourself what hidden multidimensional system is really at work here. Thanks for joining us.